So our topic today is torque and rotational equilibrium. Now, the starting point for the definition of torque is, or a good place to start, is to look at a door. And of course, to make a door rotate, you need to push on it. You need to exert a force on the door. And when you do that, the door will rotate. And the definition of torque, then, is that a torque on an object causes the object to rotate. Now, torque depends on the amount of force that you're applying, and it varies directly with that, but it also depends on the distance at which that force is applied from the axis of rotation, which in this case is the axis of the hinges. Now, in some cases, we will call that a pivot point. In some cases, we'll call it an axis of rotation. So torque depends on a force and on a distance, and it varies directly with both of them. But there is another thing that matters, and that's the angle at which the force is applied. Torque will be a maximum when the force is perpendicular to the object. It'll be 0, actually, so this is the door drawn. The rotational effect will be 0 when the force is applied parallel to the object. So we can define torque then, final definition. A torque, now this is a Greek letter tau, you could just do T if you want, as a force times a distance to a pivot, but you only get torque when the force is perpendicular to the distance. And so that means the units of torque will be newtons times meters or newton meters. We leave it as a newton meter. It's not a joule because it's not newtons times meters of displacement. It's newtons times meters of distance from the pivot. So that's our definition of torque. A simple example or two now. So let's find the net torque on this beam. Now our starting point in our solution will be to draw a force diagram. So let's draw all the forces that act on this beam. Okay, well clearly there's a weight here, 25 newtons of weight, and that'll act perpendicular to the beam. Then there is a fulcrum here, and that's clearly going to be pushing up on the object. And then the beam itself has weight, 12 kilograms, and that weight on average acts at a point called the center of mass. So the 12 G's of weight then acts at this location, the center of mass, which is halfway along the beam, where G is 9.8. This is a normal force. And then this is this weight right here. Now, because the beam's 7.5 meters long, this 12G force is going to act 3.5 meters from this end, 3.5 meters from this end. That means 2 meters from this fulcrum. It doesn't matter that the fulcrum is here. The center of mass is still at the geometric center of the beam. Okay, so now we're asked to find the net torque. So the sum of the torques will be it doesn't really matter. We can just pick a direction. Let's just take the clockwise as positive. Minus the torques counterclockwise. That's what we want to find. Now, the clockwise torque. If you lay a pencil along the beam, hold it right here, and then push downwards with this weight, you'll see that it tends to make the pencil rotate counterclockwise. This 12G force, on the other hand, tends to make the pencil rotate in a clockwise direction. So the clockwise torque is due to the beam's own weight, which is 12 G's of force. Now, a torque is a force times a distance to the pivot, and it's got to be perpendicular. So the force in this case is, Fr, the force in this case is 12 G's of weight. The distance to the pivot is 2 meters. So that's an expression for the clockwise torque. The counterclockwise torque is due to the 25 Newton weight. Now, again, a torque is a force times a distance to a pivot, force times R, and again, the force and R need to be perpendicular. They are in this case. The force is 25 newtons, and the distance is 1.5 meters from the pivot. So this will be the net resultant torque on this beam. Now, notice the normal force acts right at the pivot. Therefore, there's no distance from the pivot. Therefore, the normal force does not create any rotation. So a force acting at the pivot point produces no torque. We could just note that down at the bottom of the notes page. Force acting at the pivot produces no torque because the distance is 0. And then we said here earlier that gravity acts on average at the center of mass, at the geometric center of uniform objects. So just flashing back to our calculation, we can churn out what that number is now. Okay, so I get 197.7 Newton meters of torque. And it's in the clockwise direction, because the clockwise torque was bigger here. Now the fact that the net torque is clockwise means that the object rotates clockwise. In fact, there's a clockwise rotational acceleration. If, on the other hand, the net torque was counterclockwise, that would lead to counterclockwise rotational acceleration. Let's look at another example, one more closely related to biology. So here is your upper arm, here's your elbow joint, and here's your lower arm. The way that the lower arm rotates is your bicep muscle or your tricep muscle contracts, and then that pulls on a bone. And the place at which it pulls on the bone is a certain distance away from the joint between the two bones. That creates rotation. If we look here at the simple physical model, the bones are in clear and the muscle has got the striations in it, you can see that if there's a force applied from that muscle, when the muscle shortens, it will pull up on the bone, and that is going to create torque. The other forces that act on the arm are the weight of the lower arm, and then there's a force, a contact force here, of the upper arm pushing down on the lower arm. And so we are asked here to find the net torque on the arm given the amount of muscle tension. So holding your pencil along this lower arm structure and holding it right here, you'll see that if with your other finger you push upwards, this muscle torque tends to rotate it in a clockwise direction, and this weight tends to rotate the lower arm in a counterclockwise direction. So we're asked to find the net torque. So the sum of the torques, so I'm going to take, again, the clockwise, because I expect that's going to win, minus the counterclockwise torque. The clockwise torque is due to the muscle force. A torque is a force times a distance. We're told the tension in the muscle is 1,200 newtons of force, and we're also told that the muscle is connected 2 centimeters away, or 0.02 meters away, from the elbow joint. Now, we'll treat the lower arm as uniform, and therefore its weight is due to the weight of the lower arm. Sorry, getting ahead of myself a little bit. And a torque is a force times a distance. The force is the weight of the lower arm, which is 2 kilograms times 9.8. And then the distance, if the lower arm is uniform, the center of mass will be exactly halfway along the lower arm. That'll be 25 centimeters or 0.25 meters away from the pivot point. So this is an expression for the net torque on the lower arm. The clockwise one, again, will win. Let's calculate that. Okay, and I get 19.1 Newton meters of torque. Again, in the clockwise direction. All right. So in both of those cases, we found the net or resulting torque, and we saw that a net torque led to a rotation. Well, if the object is not rotating, then it must be that the net torque, the sum of the torques, is actually 0. Or another way to put that is the counterclockwise and clockwise torques are balanced. And this is the problem we're going to focus on for the remainder of our class today. The other condition for static equilibrium, of course, is that the forces must sum to 0. So forces up and down, forces left and right. So that actually usually translates into 2 conditions. If we think of components of force, the components are balanced both left and right, also both up and down. So let's look at an example of a system in equilibrium. So say you bend over to pick something up. It's very hard on your back, and here's the reason why. So you've got the weight of your upper body pulling down here. The center of mass of your upper body, you can see, is roughly somewhere around your chest, and that's a fairly large distance from your hip joint. The force that enables you to remain like that comes from your back, the muscles along your spine, and that's a relatively short distance away from the hip joint. So you could see this force acting in this direction has an effective distance of 5 centimeters away from the hip joint pivot, and therefore this force is going to tend to be relatively large. So we're asked to, first of all, find the tension in this muscle, and secondly, find the reaction force at the hip. We'll do that using the conditions for static equilibrium. So what do those conditions say? Well, they say that the torques have to sum to 0. So the counterclockwise minus the clockwise has to be 0, or they have to equal each other. So with this pivot point, the weight of the upper body tends to rotate us in a clockwise direction. So this is due to the weight. The spinal muscle tension passes over the top of the pivot point and therefore creates a counterclockwise torque. Now, a torque, we remember, is a force times a distance. So we actually don't know what the force is in the muscle. That's an unknown. The distance is 0.05 meters of perpendicular distance from the pivot point. So if we draw that little r vector, we see that it really is perpendicular to the force. So the force is F, that's F, and the effective distance is 5 centimeters. Now, the torque due to the weight will again be a force times the distance. They have to be perpendicular to each other. The 400 newtons is perpendicular to the 12 centimeter distance. And therefore, that's an expression for the clockwise torque. They have to be balanced, and we see that we can solve that equation for the tension in the spinal muscles. Let's work that out. Now, solving gives us a muscle force of 960 newtons. We were also asked to find the reaction force in the hip. Now, we should add that to our force diagram. Whoops, that's not what I wanted. Here we go, color. Because the hip bone will be pushing on the upper body. And there's going to be a force there that's going to maintain equilibrium. It's going to have both an X component from the hinge and also a Y component from the hip, rather, not the hinge, and a Y component from the hip. So that force, we could call it force reaction maybe. I'll call it R. So this is the force R, and it's going to be an X component of reaction and also a Y component of reaction. This force F was from the spinal muscles. That's the vector right here. So now let's apply the conditions for static equilibrium, which say the X forces have to sum to 0. Well, there's only two. There's to the right reaction force, and then there's to the left muscle force. They have to be balanced. So the X component of hip reaction just equals the muscle tension, which is 960 newtons. In the up and down direction, you've got upwards reaction Y, and then you've got downwards weight, and they have to balance. So now the Y component of reaction must be 400 newtons. And if you wanted to find the overall reaction force at the hip, you could just now express this as a resultant of 960 and also 400 newtons, just using the Pythagorean theorem. And so that works out to be just over 1,000 newtons, and then at an angle of about 22.6 degrees above the spine. That's the angle at which that hip reaction force will be applied. Okay, another biological problem here. Here we're going to stand on one foot, and the forces that act on the foot will be, first of all, a reaction force from the ground, Fn. Then there's going to be, from the foot anyway, on the foot rather, a force of tension from the Achilles tendon pulling up on the foot. And then there'll be where the lower leg contacts the foot, there'll be some sort of reaction force. And this force, you don't really know in advance which direction it's going to be. So that's a little bit of a guess in terms of the direction. So what are our forces here? Okay, so this is the Achilles tendon. Let's call that force F. This is the reaction force where the two bones meet. Let's call that force R. And so we know that this is 3 centimeters, the tendon attached from the joint. Now we know this person is 800 newtons, and that 800 newtons, if the person's at rest, that's being balanced by the normal force from the ground. Those are the only two forces that act on the person as a whole. So since the person's at rest, it must be that they're balanced, so that the normal force must equal 800 newtons of weight. When you're standing on one foot, the floor is pushing up on your foot with a force equal to your weight. So now we can use a torque equation about the center of mass and calculate the tension in the Achilles tendon. Because you see, around this pivot point, the normal force tends to create a counterclockwise torque. And a torque is a force times a distance. The force will be 800 newtons of normal force, and the distance from the ball of the foot to the ankle joint is given as 10 centimeters, or 0.1 meters. For the clockwise torque, the Achilles tendon pulling up on this side of the pivot tends to create clockwise rotation. So that's due to the tendon. A torque, by definition, is a force times a distance. The force is an unknown tension in the tendon. The distance is the 3 centimeters between the tendon and the ankle joint. Now, because the person is at rest, the net torque is 0, or those two torques are balanced. And so the net torque is 0. We can solve this for the Achilles tendon tension, and we get 2667 newtons of tension. And then we want to write the force equations to find the reaction force in the ankle joint. That's R. That again just involves the other condition for static equilibrium, which is that forces have to balance. So we've got upwards Achilles tension, we've got upwards reaction force, and we've got upwards normal force as drawn. Clearly they can't all be upwards, but having assumed that they are, what the equations will tell us is that we've done something wrong, and the reaction force is actually downwards 3467 newtons. So the lower leg is pushing down on the foot, and that makes a lot of sense. Okay, now let's try a problem that's a little bit different. We'll look at a beam problem. These sorts of structures abound. I mean, in downtown areas, you'll see panes of glass suspended by cables above buildings. In front of malls, they often hang signs this way. It's also, I suppose, a drawbridge or even a sailboat, right? This would be the mast and this would be the boom. So anyhow, it's a pretty common structure. And if we consider the forces on the beam here, well, there's a tension in the cord. There's a weight out here of the load. There's the beam weight itself. And then there's a reaction force here at the hinge, which is going to have both y and x components. So that's what the force diagram would look like typically. So this is a tension, weight of the beam, weight of the load, reaction y, reaction x. All right, so how does the analysis play out? Well, here again is a beam, so we'll start with the force diagram. Let's just get practice, go through that again. So here's the beam, so the beam has weight, and because it's 5 kilograms, that's 5 G's of weight. The load at the end is 2 kilograms, so that's 2 G's of weight. Then there's tension in the cord, reaction, 2 components of reaction at the hinge. Those are the 2 components from whatever hinge happens to be there at the connection point of the beam to the wall. So tension, so this is 5 G's of weight, or 49 newtons. This is 2 G's of weight, or 19.6. So here's reaction y and reaction x. Now, This will be our pivot point for the purposes of the torque equation. Because this thing is at rest, the counterclockwise and clockwise torques have to be balanced or equal to each other, or sum to zero. Now, with this pivot point, the two weights both tend to make it rotate clockwise. Now, because there are two weights at a different distance, we actually have to include both of them separately. So the 5Gs, and it minus just because I was making counterclockwise minus clockwise. So the two clockwise torques have minuses in front of them. So the force is 5Gs, and the distance from the pivot, well, uniform beam, half the length of the beam will be 1.5 meters over 2. So that's how far that force acts from the pivot point. The 2G of weight acts way out at the end, 1.5 meters of distance away. So that's the clockwise torque. The counterclockwise torque comes from the rope tension. Now, a torque is a force times a distance, but remember, they need to be perpendicular to each other. That means that we're going to need to resolve tension into a component that's perpendicular to this beam and another component that's parallel to the beam. Now, this perpendicular component, you can think of it as this side of the triangle, so that would be a sine 25 component. Or you can do 90 minus 25 and get 65, and you can call it a t cos 65 component. But t cos 65 and t sine 25 are exactly equal to each other. So either approach will yield the same result. So we have to take the perpendicular component of force and multiply that by the distance. Well, this force acts at a distance 1.5 meters away from the pivot point. So this is the sum of the torques, and it must be zero. This gives us an equation that we can solve for the tension. And I'm just going to highlight here that this is the perpendicular component. And that's why we had to have it in there in this case. So this is really the first problem where we had to worry about components. So let's crunch out what this number is. Okay, so we get 104.4 newtons of tension there. Now that's the first condition for static equilibrium. The second condition for static equilibrium says that the forces have to be balanced. So in the y direction, and we'll take the y direction as being upwards positive, so we've got upwards reaction y from the hinge, so this is ry, sorry. It may look like an F on the diagram, but I want it to be R. Then we've got this upwards t cos 65. Then we've got the two downwards weights. Now this is a force equation, so notice there's no distance involved. So substituting in the tension of, what was it, 104.4 newtons, we can find the reaction y component. Then in the x direction, there's only, in the positive x direction, here's my coordinate system, we have reaction x. And then in the negative x direction, we have this component of tension, which is t cos 25. And then you can solve for the x component of reaction. Okay, so solving, we find that the y component of reaction is 24.5 newtons, and then the x component of reaction is 94.6 newtons, and you can find the resultant reaction force at the hinge. And so that illustrates the main essential points that come to bear when analyzing objects in static equilibrium. We've got our definition of torque as a force times a distance. Torque makes things spin, and the value of torque depends on the perpendicular force component times the distance. Then, when things aren't spinning, torque sum to zero. If they're at rest, forces sum to zero, and torque sum to zero. And that's our lesson for today. And this is called, of course, equilibrium, because the object is not moving. And these are the conditions for static equilibrium. And we'll pick this up again in a bit more detail in class.